Hi, I'm going to present the work entitled Deep Learning for Diagonal Airlobe Crease Detection. This work has been done by researchers of the University of Las Palmas de Gran Canaria. According to the CDC, cardiovascular disease is responsible for one death every 34 seconds in the US. Furthermore, 1 in 5 heart attacks are silent. The damage is done, but the individual is unaware. The World Health Organization has also reported heart diseases as a leading cause of death globally, where ischemic heart disease exceeds by far the strokes or pulmonary disease. In 2020, Spain also reported heart disease as the most common death cause after the coronavirus. Even that the lockdown somehow protects people from physical risks, the cardiovascular disease remains as the main death cause. This situation is worldwide. This is an outer ear skin. The human earlobe is composed of areola and adipose connective tissues that lack of rigidity. Due to the absence of cartilage in the earlobe, it has an abundant blood flow and may aid in warming the ears. It turns out that if the earlobe loses blood supply, no other arteries can take over, resulting in tissue damage. Consequently, some earlobes have a diagonal crease, line, or deep fold that resembles a wrinkle. Here we can see some ear samples and 2 celebrities exhibiting the diagonal earlobe crease. According to the Stanford Medicine, when you find the sign, it has a grading system that can be linked to incidents of cardiovascular events based on length, depth, vital signs, and inclination. Due to the absence of public or known datasets, we will focus only on the detection and not on the grading. It is also known as Frank's sign because it was first described by Frank in a case of series of cardiovascular disease patients. Since then, numerous reports have been published concerning its association primarily with arteriosclerosis. While not as well known as more traditional approach, diagonal earlobe crease, also known as DELC examinations, are painless, not invasive, and simple to interpret. If its diagnostic accuracy is sufficient for decision making, it could be utilized in primary care or emergency departments. Our contributions can be summarized as follows. We propose a novel dataset with DELC ear images in the wild with 342 samples. All samples have been gathered from the internet. The dataset will be publicly available. We experimentally demonstrate that it is possible to tackle this problem by combining pre-trained backbones with a new classifier. Positive samples are those ear samples with the DLC. We conduct a search using key terms such as DLC, Frank Sign, and several celebrity names to download images. The labeling phase of ears includes trimming the ear region. We did not differentiate ear sections. The entire ear was cut off. From our understanding, deep learning algorithms can detect across a larger region. After a second stage, the subset of 342 positive DLC images is available. We have considered a publicly available AWE dataset to generate the negative subset. The AWE data collection introduces the concept of ear images captured in the wild. Emerson and his colleagues collected internet-based celebrity photos. We selected this dataset due to the nature of the gathering process, which is identical to ours. To this end, we extract images within the resolution of the DLC positive subset. Finally, to ensure no DLC positive samples were included in the selected images, we examined them to generate a 350 images subset of negative images, namely AWE prima subset. As a consequence, the study dataset comprises two in the wild subsets. Both of them are gathered from the internet. A subset of the well-known AWE dataset as the DLC negative subset and a new proposed DLC Ulpgc subset as the DLC positive subset. The proposed pipeline of the DLC detection system is shown. The device process comprises two main modules, the ear preprocessing module and the classification module. In the already mentioned first module, the DLC Ulpgc and the AWE prime dataset is generated and passed to the second module where the features are computed. Then, the implemented encoder transforms the input data into a vector of features. Initially, each input sample is sent to the encoder that has been trained to extract features. These encoders are trained on the image dataset with 1,000 distinct classes. The trainable classifier refines and condenses the previously computed features into a smaller, more specific set of features. It consists of two dense layers, each with 1,024 units. Finally, a sigmoid activation function generates the classification output. The collection under consideration contains an insufficient number of samples. For instance, nearly 350 samples per class are not adequate to train a classifier without overfitting. A strategy of augmented dataset yields 2,000 photos per class. The transformations utilized for data augmentation include random brightness, random contrast, motion blur, horizontal flip, shift, scale, and rotation. Several pre-trained encoders were compared: BGGNet, Inception V3, ResNet, Exception, and DenseNet. As aforementioned, these backbones were trained using the ImageNet dataset with 1,000 distinct classes. This table provides a summary of the results obtained of the considered backbones. Validation and test accuracy are provided to demonstrate the absence of overfitting. As expected, validation accuracy exceeds test accuracy by 1 to 3%. The table also displays the size of each backbone in millions of parameters. As can be seen, the backbone's size does not affect the model robustness. It is evident that almost all pre-trained encoders perform remarkably detecting DELC. Inception v3 achieves the best result, whereas DenseNet 169 achieves the poorest. This graph better explores the relationship between backbones and by displaying the relative performance and size. From the robustness standpoint, it is clear that Inception v3 is more than 11% superior to DenseNet, the poorest backbone. VGG 19 and VGG 16 are the most prominent models in size, while others fall between 20 to 40% below that size. It is also highlights the relative significance of size when addressing the DELC issue. As can be seen, the smaller encoder within each family usually provides a superior performance. For instance, from the DenseNet model, DenseNet 121 delivers a better outcome. The same happens with the VGG models and the ResNet models. The two top models support the most pertinent insight. An absolute difference of 1%, but the MobileNet encoder is 5.5 times smaller than the Inception v3 model. In this regard, MobileNet performs 3 times faster than Inception v3. An error analysis of their performance is necessary to determine if the performance is robust in terms of balance prediction. As here we can see the confusion matrix of the best two backbones, the Inception v3 and the MobileNet. As can be seen, both models exhibit quite balanced performance, with the MobileNet encoder being the most promising due to its performance-size trade-off. This paper presents a DELC classification analysis to determine whether or not an ear image contains frank signs. Our research has shown a relationship between the size and the performance of encoders. The report experiments reveal that ear image could be used to sufficiently complete this task. Our dataset focus on image in the wild. In our proposal is one of our main contributions. It includes the creation of a positive DELC subset and using an existing dataset to generate a negative DELC subset. We have effectively addressed this complex image scenario that requires interpretation based on encoder performance and size. The exploited encoder provides remarkable accuracy on the problem. Lightweight encoders usually perform better within the same family. MobileNet as the most promising encoder better than Inception v3 optimized pathway of diagnosis, and this line of the research presents numerous intriguing opportunities in healthcare scenarios, such as monitoring ears during aging. Thank you very much for your attention.